Cryptography with unbounded collusions and impossibility of hyper-efficient shadow tomography by Alka Chakan and Vipul Goya, and Alpa is going to give the talk.
Okay. Thanks for the intro. This is joint work with Vipul Goya. Okay, let me start by recalling a very simple principle from quantum mechanics. The no-calling principle says that given an unknown quantum state, no quantum algorithm can create two copies of it. So this very simple principle has found a lot of applications in crypto. One of the most important ones is the so-called copy protection security. So in copy protection, we encode a program as a quantum state, and our first requirement is correctness. We require that for any input x, the evaluation algorithm run on this in quantum encoding, and this input x gives us the correct output with overwhelming probability. One implication of this is that we can do this without damaging the quantum state at all. So we can use this encoding repeatedly for different inputs. Okay. So let's move on to the security definition. We will start with a simplified case. So the challenger samples a program from some distribution, and it gives a quantum encoding of it to the adversary. The adversary tries to create two entangled adversaries called pirates, and these pirates are tested by the challenger. And the precise meaning of testing will depend on the application, as we will see later on, and we require that the probability of both pirates passing the testing is at most negligible. Okay, and one specific case of this definition is the unclonable decryption keys. In this case, we are thinking of copy protecting the decryption key of a PKE scheme. So the challenger samples the quantum encoding of the secret key and gives it to the adversary, and the adversary creates two pirates, and the pirates receive challenge ciphertexts, encryption of either M0 or M1, and they try to guess which case it is, and we require that they can do so with simultaneously with probability at most 1/2 plus negligible. Okay, so these were the simplified cases where the adversary was just receiving a single program or a single decryption key. And in the full security case, we will be modeling a user who buys multiple copies of the program or some users who are colliding. So the challenger samples the secret key, and it gives k copy protected keys to the adversary. And the adversary creates k+1 pirates, and these pirates receive their challenge ciphertext, and they're trying to predict if it's an encryption of M0 or M1. And we require that this happens with probability at most 1/2 plus negligible. So baseline is 1/2 because the trivial attack is to give k keys to k pirates, and the last pirate guesses randomly. And importantly, k here is not a priori bounded. It's any polynomial, it's unbounded. Okay, so let me talk about previous work a little. So on the negative side, we know that unlearnable programs are the only programs that can be copy protected, because if some program is learnable, you don't need to try to copy it, you can just learn it. And Anant and Laplaka shows that even some unlearnable programs cannot be copy protected in the plain model. This is related to the impossibility of VBB obfuscation. Okay, on the positive side, Aronson et al. Show how to copy protect any program in the ideal classical Oracle model. This is in the simplified setting of 1 copy to 2 copy. Colangelo et al. Show how to copy protect specific functionalities like PKs and PRF keys based on IO plus LWE, and this is again in the simplified setting of 1 copy to 2 copies. And finally, recently, Louis et al. Show how to do bounded collision copy protection. In this case, the adversary receives k copies of the program, q copies of the program, but this q needs to be bounded during setup, and the parameters of the scheme will grow with q, so we cannot make it arbitrarily large. Okay, so as I said, all of the previous results are in simplified models, and there's a generic attack that works for all of them in the full security model. In fact, we don't even need to consider a single user who buys multiple copies. We can even consider like different users who have each a single copy, and they just flip a coin and measure their quantum state either in a computational basis or in the Hadamard basis. And they can just post these measurement results, which are classical, online. And these measurement results are also anonymous, so they will not be caught. And in the case of CLLZ, just 2 users colliding is sufficient, and in LLQZ, Q users colliding is sufficient. And as I said, this Q is fixed at setup, so we cannot make it too large because the parameters also grow with Q. Yeah, so in LLQZ, just Q users posting their anonymous measurement results online is sufficient to obtain a classical pirate program that anyone can download and can use to evaluate the functionality on any input or decrypt any ciphertext. So these security guarantees are not very realistic in the age of the internet. Okay, moving on to our work, we show that we can copy protect PKs, PRF signatures, and also for the first time functional encryption keys in the full security model with unbounded collision based on the same assumptions as previous work. We also show that we can copy protect any unlearnable functionality, again in the full security model, unbounded collision. This is in the classical Oracle model because of the impossible result I mentioned. And finally, we show that there cannot be a polynomial time shadow tomography algorithm. Shadow tomography is a problem from quantum theory that we will be talking about later on. Okay, so moving on to our construction. Our construction is based on coset states. A coset states consist of an equal weight superposition over all the elements of a subspace coset in F2 to the lambda. And we will also be using the so-called membership checking programs for the so-called primal and the dual cosets. And one nice property about coset states is that measuring this in a computational basis gives us a vector that is in the primal basis, meaning that it passes the verification of this program. And applying Hadamard and then measuring gives us a vector in the dual coset that passes the verification of this program. So coset states satisfy a very nice property called monogamy of entanglement. It says that given a random coset state along with the obfuscation of these membership checking programs, no polynomial time adversary can create two entangled pirates that are able to produce a vector in the primal and the dual coset at the same time. Okay, so now moving on to the construction of CLLZ, which forms the basis of our construction also, but this is only secure in the one copy to two copy setting. The copy protected secret key will be a tuple of coset states, and the public key will be the obfuscations of the membership checking programs for the primal and dual cosets. And to encrypt the message, we simply sample a random challenge R, and we output R and this obfuscated program that takes as input some vectors, and it verifies if these vectors are in the correct primal or dual cosets that depending on the bits of this random challenge that's hard-coded here. And if all the verifications pass, this program releases the hard-coded message. Okay, so there's a very simple attack here in the case of two users colliding. They get their keys, and one of them measures their key in the primal basis, just in the computational basis, and the other one applies Hadamard and that measures. And the classical measurements results that they get is sufficient to run this program with any challenge R, so they will be able to decrypt any possible ciphertext using only this classical information. And there's a similar attack for the case of LLQZ, which just uses a Q-way parallel repetition of this scheme. Given Q plus one keys, there will be a repetition of one of the keys by the pigeonhole principle, and they will be able to do the same attack to get a classical information that can be freely copied a number of times, and it's able to decrypt any ciphertext. Okay, now moving on to our solution to get full security. Our first solution step is to use pseudorandom coset states. So one issue with the usage of coset states in the previous work is that coset states are not by default collision resistant unclonable. As I said, given two copies, we can extract enough information to answer any challenge. And only existing known collision resistant unclonable states are random states or their computational versions pseudo-random random states. And there is evidence that they cannot be verified even using classical oracles. And coming back to the case of coset states, we know that a polynomial size key can only have information about polynomially many different random coset states. And when we only have polynomially many different coset states, there will always be a bigger polynomial, and if an adversary receives keys of that count, it will have some collision of coset states, and we will be able to apply the attack we just talked about. So our solution's first step is to use a PRF to compress information about exponentially many different coset states and fit it into a poly-size public key so that we will be able to ensure that there will be no collision of coset states, no matter how many copies a user receives or how many users are colliding or collaborating. So in our case, our classical secret key, which allows us to create new copy-protected secret keys, will be just the PRF key. And a particular copy-protected key will be just a random ID, and the pseudo-random coset state tuple that's generated using the PRF key evaluated on that ID. And our public key will be the this obfuscated program that will have the PRF key inside, and it will basically emulate this membership checking programs we had here by first generating the description of the code set using this PRF key and ID, and it just emulates the membership checking program afterwards. Okay, now our first contribution here is we show that pseudorandom code set states actually satisfy a collision-resistant monogamy if entanglement property. So in this case, the adversary queries the challenger with some ID, and it receives the associated code set state, and it keeps doing this for any polynomial number of times with different IDs. And it tries to create two pirates that will try to use the same code set state. So it receives multiple code set states and is trying to clone one of them. And it's allowed to choose any of these IDs here, or even IDs that are outside here. And we show that no polynomial time adversary can do this, so these pirates will not be able to answer this random challenges by outputting vectors that are in the correct coset primal or dual, depending on the bits of this challenge strings that they receive. Okay. Now, let's talk about our construction so far. We said that the quantum copy protected keys will be pseudorandom coset states with associated IDs, and public key is the global membership checking verification program. And to encrypt some message, we sample random challenge R, and we obfuscate this program that will receive the ID of the key that the user is trying to employ to decrypt the ciphertext. And it will also receive the vectors that should be in the correct cosets depending on this ID and bits of the challenge string. And if all the verification for the vectors pass, it outputs the hard-coded message. Okay, so there are a couple of challenges here. So we want to reduce to the collision-resistant monogamy of entanglement game. And to do that, we will need to enforce the adversary to copy one of the keys. And one of the issues is that all the pirates could be using different IDs, but we will need to produce two pirates with the same ID that they're using to be able to reduce the collision-resistant monogamy of entanglement game. And even then, we will need to identify which coset state tuple these two pirates are using so that we can actually do the reduction. Also, since we're using IO and not ideal obfuscation, adversaries are not necessarily using the obfuscated program. They're not necessarily running it honestly to obtain the messages. They could be learning the hidden message through other ways. So our solution, step 2 here, is to use identity-based encryption. So with each key, which has a random ID, we will also give an IBE secret key for that ID. And the ciphertext program will not directly release M here, and it will instead release the IBE encryption of M under that ID. Okay, now we know that the adversary will have k IBE keys if it has received k copy protected keys, and these IBE keys will have various IDs, ID1 through IDK. And we know that pirates must decrypt an IBE ciphertext because that's all that it's receiving. So it will use one of these IDs by IBE security because these are all only ID secret keys that it has. And at this point, we know that the adversary has k IDs and we have k+1 pirates. So two of the pirates will need to use the same ID IBE key to decrypt their challenge ciphertext. And here it's much easier to find the ID that we need to produce in the monogamy of entanglement game because there are only k choices, so we can guess it randomly. Okay, this brings us to the full construction. As I said, we will release the IBE encryption of the message here under ID. Okay, and a very high-level security sketch is that, let's say that the adversary succeeds in creating k+1 pirates. And we know that each pirate succeeds with the honest ciphertext distribution by definition of the security game. And we know that they will necessarily fail with the fake ciphertext program that actually terminates if its input ID is larger than this maximum value, because this will never be satisfied. So we know that there's a success point and there's a failure point. That means that there will be a success jump at some identity threshold between 0 and 2 to the lambda. And in fact, we know that the upper threshold is not actually 2 to the lambda by IB security. The highest ID that the adversary can decrypt is IDK. So we know that if we test them with a program that rejects if ID is larger than ID sub k, they will fail. So we know that there's a success jump point between 0 and IDK. And actually, we can show that by IB security, the success jump points can only be at ID1 through IDK. So here we only have k jump points, and we can just guess which two of the k+1 adversaries are using that repeating ID, and we can also guess that ID. We will only incur a polynomial loss. And using this and some other technical tools like compute and compare obfuscation, we will be able to extract coset vectors to get a reduction to the collision risk, the monogamy entanglement game. And this also shows that shadow tomography is impossible to solve in polynomial time, answering an open question from the quantum literature. And finally, we also construct other primitives like FE, pre-RFs, and signatures. Okay, thanks.